Hello, let's go over our first section here and our first part in forces. So let's go ahead and jump into it. So first of all, a force is just a push or a pull. Okay, so it's just pushing something, pulling something, right? An example could be gravity, it could be friction, right? I'm sure you can think of something just pulling on a rope, right? Just simple stuff, but also more complicated things like magnetism, electricity, stuff like that. The units are newtons, okay? And we abbreviate that with a capital N. So for example, if we have 5 newtons of force, that's 5N, okay? Contact force is our next type of force. We have 2 main types of forces, and a contact force is a force that requires contact. Okay, so that just means these forces require things to be touching. So an example of that would be a push, right? In order to push something, you have to be touching it, or friction would be another example. Okay. Now, unlike contact forces, field forces do not require contact. Okay, so they don't require contact. They are just set up so that if 2 objects are maybe near each other or even far away, that force applies. The maybe most obvious example would be gravity, right? Think about that. If you jump, gravity still pulls on you, right? You don't, if you stop touching the earth, gravity doesn't stop pulling on you, right? Even in space, gravity is still pulling on you a little bit, okay? Another example would be the electromagnetic force, okay? Just think magnets, right? Magnets don't have to touch each other to act on each other. They just have to be close. So next thing, force diagrams, okay? This is a diagram that shows forces. It's also called a free body diagram. Sometimes you may see it abbreviated as FBD. Okay? Now, why are these so important? They're so important because they show what's happening, right? It's a great way to visualize all the forces in one spot, okay? So, in order to draw a free body diagram, you must first identify all the forces acting. So, if we wanted to draw a free body diagram on a car, the first thing we want to do is just draw a car, right? Now, you'll notice that that doesn't really look like a car, but that's okay. In physics, everything is a box, okay? So, we just have a box here, and that's all we need. Now, we got to think of all the forces that are acting on a car, okay? So, think of what's maybe the force pushing down on the car, right? That would be gravity. And so we label gravity F and then a little g, okay? So F for force, little g for gravity, okay? Now, there is a force coming from the ground pushing up, right? You'll notice that we know that the car is not falling through the ground, so there has to be an upward force counterbalancing my gravity force, okay? And we call that F capital N. That stands for the normal force, okay? And the way I remember this is it would be really unusual, not normal, if I fell through the floor, right? So the normal force is what normally happens when you stand on the floor. It holds you up, right? Then we have some other forces, okay? The car is maybe accelerating forward, and so it has some force here. I'm just going to put F of the engine, okay? So there's some forward force pushing it forward. And then we also have a force that's pushing backwards. What's the force that slows down the car? Okay, hopefully you got it. Friction. So F, little f. You could also say air resistance would be another example of a force that is resisting. But we're just going to stick with these 4, kind of the fundamental forces that we often see. Okay? So here we drew the gravitational force, we drew the upward force, remember that's the normal force, Fn, and then we drew the backwards force of friction, so that's going to the left. Now, these are all vectors because they represent the direction these forces are actually pushing, right? So it has both that magnitude, which is the number or the variable we list here, but then also the direction that we've pointed it in. Okay, so before 1600, what was believed to be the natural state of most objects? The idea was that objects tend to slow down and stop. Now this makes sense because when you look at things, if you see a ball rolling, you assume that it's eventually going to stop rolling, right? But Galileo pointed out that that's not actually true. What's happening is friction is causing that to slow down and stop. But in reality, objects tend to continue doing what they are doing unless there is a force. In other words, if I throw an object, it's going to keep going in that exact same direction forever until there's a force. For example, gravity, friction, all that good stuff. A better way to visualize this is if you throw something in space, what's going to happen? It's just going to keep going in that direction forever, right? We don't have friction to slow it down, so it's just going to keep going, okay? So this is called inertia. So inertia is Newton's first law of motion. It just says that objects tend to continue doing what they're doing unless there's a force. So if there's no force, it will continue with a constant velocity forever. If there is a force, then it would change, right? Alternatively, if an object is sitting still, it's going to sit still forever until there's a force acting on it. So that's just inertia, right? So that's why Newton's first law is also referred to as the law of inertia. Now, how do we determine the acceleration of an object? Okay, acceleration of an object is dependent on two things: the F net and the mass, okay? So if the F net increases, in other words, the total force, right? If that total force increases, then we know the acceleration increases. But if the mass increases, right, if I have a bigger thing, it's going to be harder to move. Therefore, the acceleration decreases. So the external force, these are forces that do not connect. Okay. Now, obviously, if I'm sitting at a table right now, right, a table has internal forces that keep that table together, right? If those forces stopped working, the table would fall apart. But when we're looking at our F net and M and all that good stuff, we're not really worried about those internal forces. We're just worried about, am I pushing a table, right? Am I pushing a desk? So it's those external forces, forces that are acting from somewhere else, okay? The net external, we label that F net. And so that's the sum of all the forces. Now, the thing that's important is that since these are vectors, we need to kind of add them up in a chart, right? We cannot just add them up straight. We can't just do 1 plus 2 plus 3 plus 4 because these are vectors. They have a direction. So I want to think about, okay, in the y direction, maybe I have Fn is positive, but I have negative Fg, right? In the x direction, maybe I have a positive, let's say, force from the engine, and then I have a negative Ff, okay? And so then I can find this total. Now this total Fx and Fy, these are actually two parts. So I have a Fx here, Fy here. These are two parts. Now if I want to find my total, this right here, that is my F net, okay? And so hopefully you'll notice that this is a right triangle. So in order to find my F net, I need to use the Pythagorean theorem, okay? Now, oftentimes you'll see that maybe the Fy's are 0. Okay, so if something's not accelerating in a particular direction, then we know that that Fy has to be 0, in which case this is equal to my F net, which makes sense, right? If Fy is 0, then this goes away, and F net squared equals Fx squared, right? So oftentimes you'll see that, but we do need to know just in general how to find our F net, okay? So for example, here we have something that looks like this. We want to find the F net on this box. So what we need to do is make our Fx, Fy chart. So in the x direction, let's go ahead and set our axes just to make sure. Let's do normal math axes. So In the x direction, I have 950 minus 1520. And then in the y direction, I have 5120 and 4050. Okay, and so in the x direction, I'm going to have something like negative 570. And then in the x direction, I'll have something like 1070. Okay, those are both newtons. And then to find our total F net, I just need to make my triangle. So I have x, I have y, I have 570 and 1070. And then to find F net, I just have F net equals square root of 570 squared plus 1070 squared. Okay? And so we'll get some number for that. And make sure you write your newtons. Okay. The important thing is not this algebra step, but just showing you where that's coming from. Okay. Now, hopefully this should look familiar. This is similar to maybe what we've done a little bit with our 2D motion. But that's how we would find our F net. Now, the second one, we have a force as an angle of 37 degrees above the horizontal, and gravity also pulls down with a force of 2 newtons. Here we're still finding the net external force. So let's go ahead and draw our Fx and Fy chart. Now this one is at an angle, so it's going to have both a y component and an x component. Okay, so in the y side, remember it's the same as we do for velocity when we're splitting a velocity into components. So it's going to be the magnitude. Our magnitude is just a number. Then either sine or cosine, and then the angle. Okay, so for this one, it's going to be 5 since it's y. Remember, y comes second in the alphabet, which means we use sine. 5 sine 37. Okay, and then x is going to be very similar. 5 cosine 37. Okay, and then we also have a downward force of 2 newtons, so I'm going to subtract 2 newtons. Okay, now in the x direction, that's going to give me something like 4. And then in the y direction, I'm going to have something like 3 minus 2, which equals 1. Okay, so I have something that looks like 4, 1. And then I want to find my F net. This here is my F net. So F net equals root 1 squared plus 4 squared, which equals square root of 17. Okay, square root of 17 newtons. So it's not too hard. It should hopefully be a bit of a review. What we're really doing is just finding sort of vector sums. Okay. Remember, we need to split our x and y's into separate parts so we can treat those separately because it's a vector. If you have any questions, let me know. And that's kind of just the basics of forces. And I will see you hopefully in the next video for the next section where we kind of actually start finding out a little bit more about forces. Thanks so much.